Microsoft Azure Machine Learning Deep Dive, the complete lifecycle from data to production AI.
Hello and welcome. In this deep dive, we will explore Microsoft Azure Machine Learning as a complete platform for building, training, deploying, monitoring, securing, and governing machine learning systems at enterprise scale. Azure Machine Learning is designed to support the entire machine learning lifecycle, including data preparation, experimentation, training, deployment, monitoring, governance, responsible AI, and generative AI application development. The platform supports collaboration across data scientists, ML engineers, application developers, and enterprise platform teams. Its primary value is helping organizations move from isolated experiments toward repeatable, scalable, secure, and production-ready AI systems. Azure Machine Learning is a cloud service that accelerates and manages machine learning projects across the full lifecycle. Teams can build models directly in Azure Machine Learning or bring models created with open source frameworks such as PyTorch, TensorFlow, Scikit-learn, XGBoost, LightGBM, ONNX, and MLflow compatible workflows. The platform supports both traditional machine learning and modern generative AI workflows through capabilities such as model catalogs, prompt flow, and tools for building applications powered by large language models. Azure Machine Learning also provides MLOps capabilities for monitoring, retraining, redeploying, and governing models in production environments. This makes the platform valuable for organizations that require scalable, auditable, and enterprise-grade AI operations. The Workspace is the top-level resource in Azure Machine Learning. It centralizes jobs, logs, metrics, outputs, models, environments, components, data assets, data stores, and compute resources. The Workspace also maintains lineage and history tracking for experiments and deployments, which is critical for reproducibility, auditability, and enterprise MLOps practices. A Workspace provides teams with a shared environment where they can collaborate securely while maintaining visibility into the full lifecycle of machine learning assets. Azure Machine Learning Workspaces also integrate with supporting Azure resources such as storage accounts, Azure Container Registry, Key Vault, Application Insights, and managed compute infrastructure. Azure Machine Learning supports multiple development approaches because machine learning teams often include professionals with different technical backgrounds and responsibilities. Azure Machine Learning Studio provides a browser-based experience for notebooks, AutoML, designer pipelines, prompt flow, data labeling, jobs, assets, and deployments. The Python SDK v2 supports code-first development for jobs, pipelines, components, models, and endpoints. The Azure CLI v2 enables automation through YAML-based definitions and command line operations. Azure Resource Manager REST APIs provide the underlying control plane foundation for enterprise automation and custom platform tooling. Although these interfaces target different users and workflows, they all share the same Azure Machine Learning v2 concepts and asset model. The Azure Machine Learning v2 platform standardizes machine learning operations around reusable assets, declarative YAML schemas, and consistent APIs. YAML schemas define jobs, pipelines, components, environments, endpoints, and deployments. Training logic and scoring logic remain inside Python or other scripts, while infrastructure and orchestration definitions remain declarative. The CLI v2 is especially useful for CI/CD pipelines, automation, and infrastructure operations. The SDK v2 is commonly used for experimentation, reusable pipeline composition, orchestration, and advanced workflow development. Both SDK v2 and CLI v2 share common concepts for jobs, pipelines, environments, endpoints, components, and models, improving consistency across development and operational workflows. Azure Machine Learning Studio brings together code-first and no-code experiences in one browser-based workspace. Users can write and run notebooks, visualize, run metrics, use the designer to build drag-and-drop machine learning pipelines, run automated machine learning experiments, and coordinate data labeling projects. The studio also helps teams browse and manage project assets such as jobs, data, models, components, environments, and endpoints. This is useful because not every stakeholder works only in code. A data scientist may use notebooks, a business analyst may review experiment metrics, and an ML engineer may manage deployments. The studio becomes the visual control center for collaboration, experimentation, asset tracking, and operational management. Compute is one of the most important foundations of Azure Machine Learning. A compute instance is a fully managed cloud workstation used for notebooks, development, debugging, testing, and lightweight training. A compute cluster provides scalable CPU or GPU resources for larger training jobs and can scale based on workload demand. Kubernetes clusters can be used for deployment scenarios where teams need more control over infrastructure and runtime environments. Attached compute allows organizations to connect existing compute resources to a workspace for training or inference. Serverless compute can reduce operational work by allowing Azure Machine Learning to manage compute lifecycle tasks for supported workloads. Development usually starts with a compute instance or a local environment. A compute instance is often the fastest way to begin because it includes Azure Machine Learning tooling, notebook support, Jupyter Lab access, and direct integration with a workspace. Users can also work from Visual Studio Code, either locally or connected to a cloud compute instance. Local environments provide maximum control over dependencies and development tools, but they require more setup and maintenance. Data science virtual machines provide pre-configured data science tooling and can be useful for teams that need custom development environments. The right choice depends on speed, control, cost, governance requirements, and team standards. Data management in Azure Machine Learning is built around data assets and data stores. Data assets can represent URI files, URI folders, ML table assets, and primitive input values used in jobs and pipelines. URI files and folders are recommended for many common scenarios because they map clearly to storage locations and can be mounted or downloaded by compute resources. ML table is useful for tabular data scenarios such as AutoML, parallel jobs, and advanced workflows. Data stores securely store connection information for Azure Blob Storage, Azure Files, Azure Data Lake Storage, and Azure Data Lake Storage Gen 2. This helps teams access data without hard coding credentials in training scripts. Data assets make machine learning projects easier to repeat, govern, and audit. Instead of remembering long storage paths, teams can register important data sets with friendly names, descriptions, tags, and versions. A data asset references the data location and stores metadata, while the data itself can remain in its existing storage location. This supports lineage because jobs can record exactly which data asset version was used for training, evaluation, or scoring. The Azure Machine Learning documentation example uses a credit card default dataset, registers the raw data, cleans it, and creates a new version for training. This shows how raw data can evolve into training-ready data while remaining traceable across the lifecycle. Environments define the runtime used for training and inference in Azure Machine Learning. They include software packages, environment variables, Docker images, conda configurations, and other runtime settings required by training or scoring scripts. Azure Machine Learning supports both curated environments provided by Microsoft and custom environments created by users. Curated environments help teams start quickly with optimized configurations for common frameworks such as PyTorch, TensorFlow, Scikit-learn, and CUDA-based GPU workloads. Custom environments are important when projects require exact dependency versions, proprietary libraries, or specialized runtime configurations. Version environments improve reproducibility, portability, governance, and auditability across different compute resources and deployment targets. Training workloads in Azure Machine Learning are typically submitted as jobs. A command job runs a script or command using specified inputs, outputs, compute targets, and runtime environments. In the documentation example, the training script reads the credit card dataset, splits it into training and testing sets, trains a gradient boosting classifier, logs metrics with MLflow, and registers the trained model. This pattern is powerful because the job definition separates infrastructure orchestration from the actual training logic. Teams can change compute resources, parameters, environments, or datasets without rewriting the core script. Jobs also capture logs, metrics, artifacts, and outputs automatically for monitoring, reproducibility, and later analysis. Azure Machine Learning supports scalable training patterns beyond simple single-node workloads. Compute clusters can scale horizontally for larger CPU and GPU training scenarios. Distributed training is supported through frameworks such as PyTorch Distributed, TensorFlow Distributed, MPI, and Horvath-style patterns. The documentation also includes examples of distributed PyTorch and TensorFlow training jobs running across multiple GPU instances. Apache Spark workloads can run through serverless Spark Compute or Synapse Spark pools for large-scale data engineering and machine learning scenarios. These capabilities are important when teams work with large datasets, deep learning models, forecasting across many entities, or highly parallel workloads. The platform allows organizations to begin with smaller experiments and scale compute resources as workloads become more demanding. Automated machine learning, often called AutoML, helps accelerate model development by automating portions of the experimentation process. In traditional machine learning workflows, data scientists often spend significant time selecting algorithms, testing feature engineering strategies, and tuning hyperparameters. AutoML can automatically evaluate combinations of models, featurization approaches, and optimization strategies to identify strong candidate models more efficiently. It can be used through the Azure Machine Learning Studio interface or through SDK and CLI workflows. AutoML also supports advanced scenarios such as computer vision tasks, including object detection and image classification, where GPU compute and hyperparameter sweeps may be used. AutoML does not replace machine learning expertise, but it significantly reduces repetitive experimentation work and speeds up early-stage model development. Hyperparameter optimization is another major training capability in Azure Machine Learning. Many machine learning models depend heavily on parameters such as learning rate, batch size, optimizer selection, regularization strength, tree depth, or the number of estimators. Azure Machine Learning supports automated sweep jobs that can explore parameter ranges using strategies such as random sampling, grid sampling, and Bayesian optimization. Results can be visualized directly in the studio to compare model performance across trials. For image and deep learning workloads, the documentation also describes automated and manual sweep patterns, including trial limits, concurrency settings, and early termination policies that stop poorly performing runs to save compute resources. This allows teams to use infrastructure more efficiently and evaluate experiments systematically instead of manually running large numbers of independent training jobs. Experiment tracking in Azure Machine Learning is deeply integrated with MLflow. MLflow can automatically log parameters, metrics, artifacts, model outputs, dependencies, and visualizations during training and pipeline execution. This is essential because machine learning development is highly iterative, and teams must be able to explain how a model was produced and why it was selected. Users can compare runs, inspect logs, review evaluation metrics, and trace performance differences across experiments. The Azure Machine Learning documentation examples use MLflow autologging to capture training details automatically during jobs and pipelines. This creates a reproducible history that links model performance back to the exact training data, code version, parameters, runtime environment, and compute configuration used during training. Model registration moves a trained model into a managed and versioned lifecycle. A registered model becomes a reusable asset stored either in a workspace or in a centralized Azure Machine Learning registry. Azure Machine Learning supports multiple model formats, including custom models, MLflow models, and Triton models for high-performance inference scenarios. Model registration helps teams organize versions, manage approvals, and prepare models for deployment workflows. Registering models is considered a best practice because deployment pipelines rely on stable and versioned model references. It also improves lineage and governance by making it possible to trace a deployed production model back to the original training job, dataset version, runtime environment, code snapshot, and evaluation metrics. Azure Machine Learning registries extend asset management beyond a single workspace. Registries can centrally store and share models, environments, components, and other reusable machine learning assets across multiple workspaces and regions. This is important because many organizations separate development, testing, staging, and production environments for security, compliance, operational governance, or billing reasons. A model may be trained in one workspace, validated in another, and then deployed into production from a centralized registry. Components and environments can also be promoted across environments to standardize workflows and reduce duplication. Registries support multi-region replication, enabling lower latency access to shared assets across geographically distributed teams and workloads. This architecture helps organizations implement scalable and standardized enterprise MLOps practices. Deployment in Azure Machine Learning is built around endpoints and deployments. An endpoint provides a stable HTTPS interface where applications send input data and receive predictions from deployed models. A deployment defines the actual runtime configuration behind the endpoint, including the model, compute resources, environment, scoring script, instance type, scaling settings, and instance count. Azure Machine Learning supports online endpoints for low latency real-time inference and batch endpoints for asynchronous scoring across large datasets. This architecture separates the client-facing endpoint from the underlying deployments, allowing multiple deployments to exist behind a single endpoint. Teams can safely perform staged rollouts, /B testing, blue-green deployments, traffic splitting, and controlled production updates without disrupting client applications. Managed online endpoints are the recommended deployment option for many real-time inference scenarios because Azure Machine Learning manages the underlying serving infrastructure automatically. Teams can deploy models on CPU or GPU-backed machines without directly managing Kubernetes clusters or virtual machine infrastructure. Managed online endpoints support enterprise production capabilities such as auto-scaling, authentication, logging, monitoring, model data collection, safe rollout strategies, traffic mirroring, and cost analysis at both the endpoint and deployment level. Azure Machine Learning also simplifies deployment for MLflow compatible models because the scoring environment and inference configuration can often be generated automatically in supported scenarios. This reduces operational complexity and helps teams move models from experimentation into production more quickly and consistently. Batch endpoints are designed for workloads where scoring does not need to happen in real time. Instead of processing one request at a time with immediate responses, batch endpoints process large datasets asynchronously at scale. This is useful for scheduled scoring jobs, offline prediction pipelines, recommendation refreshes, financial risk scoring, document processing, forecasting workloads, and large-scale data enrichment tasks. Batch endpoints can run on Azure Machine Learning compute clusters and support both model deployments and pipeline component deployments. They can also integrate with orchestration services such as Azure Data Factory, Microsoft Fabric, or enterprise data pipelines. Batch inference is often the preferred choice when throughput, cost efficiency, scheduling flexibility, and parallel processing are more important than low latency responses. Azure Machine Learning supports safe deployment strategies that reduce production risk during model updates. One common pattern is blue-green deployment, where an existing stable deployment operates as blue while a newer candidate deployment operates as green. Traffic can then be shifted gradually, such as moving from 100% blue traffic to a smaller percentage on green for controlled validation. If the new deployment performs well under real production traffic, the rollout can continue until green becomes the primary deployment. If problems occur, traffic can quickly be routed back to the stable deployment. Azure Machine Learning endpoints also support traffic splitting, testing, staged rollout, and deployment isolation. These capabilities are essential for reliable, responsible, and enterprise-grade production model operations. Monitoring becomes critically important after deployment because model behavior and data quality can change over time. Azure Machine Learning integrates with Azure Monitor, Application Insights, and model monitoring capabilities to help teams observe production systems continuously. Online endpoints can collect inference data, logs, metrics, latency information, and model inputs for analysis. Built-in monitoring capabilities can track signals such as data drift, prediction drift, feature distribution changes, and data quality issues. Monitoring jobs can run on scheduled intervals and compare recent production data against baseline or reference datasets. When thresholds are exceeded, alerts and notifications can inform the responsible teams that investigation, retraining, or model replacement may be required. This helps organizations maintain model reliability, accuracy, and operational trust over time. Pipelines automate complete machine learning workflows from data preparation through deployment. A pipeline breaks a machine learning project into individual steps, such as ingestion, cleaning, feature engineering, training, evaluation, registration, and deployment. Each step runs as a reusable component with clearly defined inputs and outputs. Azure Machine Learning manages execution order and dependencies automatically, so workflows execute consistently and reliably. Pipelines improve efficiency because outputs from unchained steps can be cached and reused instead of recomputed. Different steps can also run on different compute resources optimized for specific tasks. This modular architecture supports standardized MLOps practices, scalable team collaboration, reproducibility, automation, and cost-aware machine learning operations. Components are reusable building blocks used inside Azure Machine Learning pipelines. A component contains metadata, interfaces, input and output definitions, runtime environments, and the code or command body that performs a task. Components can represent data preparation, feature engineering, training, evaluation, scoring, validation, or model registration steps. They can be defined using Python SDK workflows or declarative YAML specifications and then registered as reusable assets inside a workspace or registry. Reusable components reduce duplicated work and allow organizations to standardize common machine learning tasks across many projects. In larger enterprises, shared components help enforce governance, consistency, testing standards, and repeatable MLOps practices across distributed teams and production environments. MLOps in Azure Machine Learning connects experimentation, deployment, monitoring, and operational governance into a unified lifecycle. The platform supports Git integration, MLflow experiment tracking, scheduled pipelines, Azure Event Grid triggers, GitHub Actions, Azure DevOps, and CI/CD automation workflows. Jobs automatically capture code snapshots, logs, metrics, artifacts, outputs, environments, and lineage information during execution. This creates traceability and auditability across the complete machine learning lifecycle. Azure Machine Learning pipelines and registries also help standardize promotion processes between development, testing, and production environments. It is about ensuring that models can be reproduced, validated, monitored, retrained, promoted, governed, and eventually retired in a controlled and repeatable way. Security is a major architectural focus within Azure Machine Learning. The platform integrates with Azure Role-Based Access Control, Managed Identities, Azure Key Vault, Azure Container Registry, virtual networks, private endpoints, private DNS zones, and network security groups. Workspaces can restrict public network access and use private connectivity for sensitive enterprise environments. Managed virtual networks can simplify network isolation by allowing Azure Machine Learning to manage isolation rules and private connectivity for workspace resources and manage compute. Azure Machine Learning also supports customer managed keys, secure storage integration, and enterprise governance controls. These capabilities are especially important for organizations working with regulated data, intellectual property, financial workloads, healthcare systems, or internal enterprise AI platforms. Secure inference requires attention to both inbound and outbound network communication. For managed online endpoints, inbound access can be restricted by disabling public network access and exposing endpoints only through private endpoints within a virtual network. Outbound communication from deployments can also be secured through managed virtual networks, firewalls, and private connectivity to approved Azure services. This becomes important when deployed models need secure access to private storage accounts, Azure AI services, internal APIs, or protected enterprise resources during inference. Azure Machine Learning also supports secure Kubernetes-based inference environments for organizations that require additional infrastructure control. Strong network architecture helps reduce data exposure risks while still allowing production AI systems to operate reliably and securely. Azure Machine Learning integrates with a broad ecosystem of Azure services to support complete enterprise AI architectures. Azure Synapse Analytics and Spark services can support large-scale data engineering, analytics, and distributed processing workloads. Azure Arc helps extend Azure management and machine learning capabilities into Kubernetes and hybrid environments. Azure Blob Storage, Azure SQL Database, Azure Cosmos DB, and Azure Data Lake Storage support different enterprise data storage patterns. Azure App Service and container platforms can host AI-powered applications and APIs. Microsoft Purview can help organizations discover, classify, and govern enterprise data assets across environments. These integrations are important because production AI systems rarely operate in isolation and typically depend on broader data, security, application, networking, and governance ecosystems. Generative AI capabilities are now an important part of the Azure Machine Learning ecosystem. The model catalog helps teams discover, evaluate, and deploy models from providers such as Microsoft, Azure OpenAI, Meta, Mistral, Cohere, NVIDIA, Hugging Face, and other ecosystem partners. PromptFlow supports the lifecycle of large language model applications by helping teams prototype, orchestrate, evaluate, test, and deploy prompt-based workflows. Azure Machine Learning Studio provides tooling for experimentation, monitoring, and operational management of generative AI workloads alongside traditional machine learning workflows. Azure AI Foundry also provides experiences for working with foundation models and AI applications depending on project requirements. These capabilities expand Azure Machine Learning from traditional predictive analytics into modern enterprise AI and large language model application development. Responsible AI is an important theme across Azure Machine Learning. The platform supports fairness, explainability, tracking, auditability, lineage, and governance across the model lifecycle. These capabilities are especially important when models influence decisions in areas such as finance, healthcare, hiring, operations, or customer experience. Responsible AI is not only a dashboard or a final review step. It requires traceable data, explainable experimentation, monitored deployment, access control, clear ownership, and documented decisions. Azure Machine Learning provides many of the technical foundations teams need to build, evaluate, operate, and govern models responsibly. Business continuity and disaster recovery require careful planning because Azure Machine Learning depends on several supporting Azure resources. A workspace uses associated services such as Azure Storage, Azure Key Vault, Azure Container Registry, and Application Insights. Some resources are managed by Microsoft, while others are created in the customer subscription and require customer planning. Organizations should not assume that every workspace artifact, run history, or metadata record is automatically protected by full cross-region failover. A strong recovery strategy should include source control, infrastructure as code, registry-based asset promotion, resilient storage design, repeatable deployment pipelines, and documented recovery procedures. A practical Azure Machine Learning workflow usually follows a clear life cycle. First, create a workspace and configure secure compute. Then upload, register, or reference data through data stores and data assets. Next, prototype in notebooks, Visual Studio Code, or local environments, define reusable environments, and submit training jobs. After training, track metrics with MLflow, compare experiments, register the best model, and deploy it through online or batch endpoints. Once the model is in production, teams monitor quality, latency, drift, data issues, and operational signals. Over time, retraining, redeployment, and governance can be automated through pipelines and MLOps practices. The main takeaway is that Azure Machine Learning is not only a model training service, it is a lifecycle platform for enterprise machine learning and AI. It gives teams structured assets, scalable compute, managed environments, experiment tracking, model registration, endpoints, pipelines, monitoring, security, governance, and integration with both open source and Azure native tools. Its greatest value appears when organizations need repeatability, traceability, collaboration, and production control. For teams moving from prototypes to real AI systems, Azure Machine Learning provides a strong foundation to build responsibly and operate at scale. Thank you for watching. See you in the next video.